Okay, hello everyone. This is Shailza Kanwar, Assistant Professor in IT Department at Ajay Kumar Garg Engineering College. So today's I will cover division algorithm of computer organization and architecture subject. So what is division algorithm? It is a process of successive compare, shift and subtract operations. There is a recursive formula. We will do successively compare, then shift and subtract again and again. So binary division is a simpler than decimal division because the quotient digits are either 0 or 1 and there is no need to estimate how many times the dividend or partial remainder fits into the divisor. So this is a simple example of binary division. So for example, here divisor is B 1 0 0 0 1. So the value of this is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3 and 2 raised to power 4. So 2 raised to power 0 is 1 and 2 raised to power 4 is 16. So 16 plus 1 is 17. So here divisor is 17 and the value of this is 2 raised to power 0, 2 raised to power 1, 2, 3, 4, 5, 6, 2 raised to power 6 plus 2 raised to 7 plus 2 raised to power 8. So the value of this number is 148. So here dividend is 148 and divisor is 17. So if we divide 148 with 17, we will get, we simply divide this, we will get 17 to the 34. 4 minus 3 is 2. So finally we will, after performing this division, we will get remainder of 6 and the quotient is 26. This is normal binary division, normal decimal division. If we have to perform this is in binary form, there is a thumb rule that our dividend should be, so the quotient is stored in Q register, dividend in A register, this is the dividend, and the divisor in B register. So as I said, the thumb rule is dividend should be greater than divisor. So in divisor we have value of 17, first 5 bits is 17 and these first 5 bits 1, 2, 3, 4, 5, these 5 bits are, but now what is the value of these 5 bits? It is 0, 1, 1, 1, 0. So it is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. So it is 0 plus 2 plus 4 plus 8. So it is 14. Now 14 is smaller than this 17. So we can't perform here division. So we will take 1 0 from here. Now we will check the value of this. Now the value of this is 0, 1, 1, 1, 0, 0. It is 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2, 2 raised to power 3, 2 raised to power 4. So it is 0 plus 0 plus 2 raised to power 2 is 4 and 2 raised to power 3 is 8 and 2 raised to power is 4 is 16. So it is 28. Now 28 is greater than the 17. Now we can perform the division. So we will put now we will shift right B and subtract. So B 1 0 0 0 1 into 1, we will get here 1 0 0 1 and we will perform simple subtraction here. Now 0 minus 1 is 1 with borrow of 1. So 0 minus, so now if we have to borrow, we will take the values till we get 1. Now 1 0 0 is 4 and here the subtraction part is 0 0 1 which is 1. So 4 minus 1 is 3. So we will write here 1 1 0. Now next is 1 minus 0 which is 1 and 1 minus 1 is 0. Now we will again check this remainder. This is called the partial remainder. We will again check. This is called partial remainder. we will check the 7 bits value of remainder whether it is greater than b or not. If we calculate this value will get greater than this b value. So we will further perform this subtraction operation. Before checking the 7 bits value, we have to drop one 0 from here. If the value is greater than, we will put 1 here in quotient and subtract this divisor part here. After dividing this, we will get the value 0 minus 1. Again, we have to borrow from here. So, as previously I said, we will take these two values 1 0, which is 2, and this is 1. 2 minus 1 is 1. So, we will write here 1 0 1, which is 1, and 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0. So, this is our remainder. We will drop 1 0 from here. Now, we will check this 6 bits. We will check this remainder whether it is less than b or not. If it is less than, then we will put 0 here and enter 0 and we have to shift right b. Now, again we will subtract and check the remainder. If remainder is greater than b, then we will shift right b and subtract, enter 1 in q. Now, what is happening here? Here the remainder is less than b. So, we have to drop down one more 0 from here. Now, before dropping down one more 0 here, we have to put 1 0 here in the Q register. Now, after checking this value, this remainder value, we will get to know that it is greater than b. So, we will shift right b here and add 1 in Q. Now, we will again perform subtraction. After performing the subtraction, we will get this value, which is 0 0 0 1 1 0. It is actually 2 raised to 0, 2 raised to 1, 2 raised to 2. So, it is 4 plus 2, which is 6. So, 6 is smaller than this. So, we will drop 0 from here. After dropping this 0 here, we will check whether it is greater than b or less than b. So, after checking, we will get to know it is less than b. So, we will put one more 0 here, and this is the final remainder. Now, what is the value of this final remainder? It is 2 raised to power 0, 2 raised to power 1 plus 2 raised to power 2. So, it is 4 plus 2, which is 6. So, this is the final remainder, and this is 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2 raised to power 2 plus 2 raised to power 3 plus 2 raised to power 4. So, it is 2 plus 8 plus 16. So, it is 26. So, our quotient is 26. So, this is a simple binary division. Now, how our computer or processor performs this binary division in its ALU part. So, here is the hardware implementation for this signed magnitude data, where sign means it has sign plus and minus. So, in hardware implementation, when the division is simply implemented in a digital computer, it is convenient to change the process slightly. We have changed our convenient process. Our convenient process is this. We have changed this process slightly. So, instead of shifting the divisor to the right, the dividend or partial remainder is shifted to the left, thus leaving the two numbers in the required relative position. Now, after that, subtraction may be achieved by adding a to the 2's complement of b. Now, for subtraction, we are adding 2's complement. 2's complement of b is minus b. So, here we are subtracting only by taking the 2's complement of b and adding that part to the a. The information about the relative magnitude is then available from the AND carry. And the hardware for implementing the division operation is identical to that required for multiplication. And the divisor is stored in B register. We have B register. So divisor is stored in B register and its sign bit is stored in BS. After performing the division, the quotient is in Q and the final remainder is in A. So after performing some division process, we will get the quotient is in Q register and it's also has a QS bit for sign purpose. And the sign of the result is transferred into Q to be part of the quotient, whether it is negative or positive depending upon the initial values. A constant is set into the sequence counter SC. There is also special sequence counter SC which to specify the number of bits in the quotients, and the sequential counter is initialized by taking the values number of bits in Q register. Now here the Q register which is used to sequential counter bits is actually it is initial phase. We store the value of dividend in A and Q register. A register is there and Q register is there. If our dividend is of double length, then we will store partial value in this A register and partial sequence in Q register. Both registers have sign bit. Sign bits are stored in AS and QS register respectively, and the number of bits in Q registers are used to initialize sequential counter. So since an operand must be stored with its sign, one bit of the word will be occupied by the sign and the magnitude will consist of n-1 bits. If A is greater than equal to B, then the divide over flip-flop DVF is set and the operation is terminated prematurely. This comes from the thumb rule that there should be no division overflow. If our dividend is smaller than divisor, then we can't perform division algorithm because there is a division overflow. So if A is less than B, there is no division overflow, no divide overflow. So the value of dividend is restored by adding B to A. That's why due to this reason, this is called as the restoring algorithm. So this is a flow chart for divide operation and it is the restoring algorithm. So as I previously told, dividend is stored in AQ because our dividend is of double length. So and our register's capacity is limited. So we stored the dividend in two parts A and Q, and divisor is stored in B register, and their sign bits are stored in AS, QS and BS register respectively. Now we have to first come from this part. Here we have to check the overflow, divide overflow. So and also to check the sign of quotient. So the quotient sign can be obtained by XORing the sign bit of dividend and sign bit of divisor. We will XOR this, and this sign bit sign is stored in QS register of Q register. It is also the used to store the sign bit of quotient register, and the sequential counter is initialized by using the n-1 bits of Q register. Now n-1 is here because one bit is for sign bit and the rest are remaining n-1. So we will store this value n-1 in sequential counter. After that we will perform EA is equal to A plus B complement plus 1. Now this is 2's complement. Actually we have to perform A minus B, but processor perform A minus B in the form of A plus 2's complement. After that, this if E is flip-flop to hold the carry. So after performing this operation, there is some value on E. We will check the value of E. If it is 0, so first we will check. If it is 1, it means A is greater than B. EA will get A plus B, and the DVF, divide overflow, is set to 1. It means there is a divide overflow. We can't perform this division operation. So here the algorithm will end prematurely. Now second part is, if E is equal to 0, it means A is less than B, and we can perform the division algorithm, or we can perform the divide operation. So here again EA will get the value of A plus B, and the divide overflow is set to 0. After that we will go in this part. Here this is a shift left operation. This is a simple shift left. We have to shift left one bit from A to E, and each bit from here in this EAQ. After that we will check the value of E again here. If the E is equal to 0, then we have to perform EA is assigned to A plus B plus 1. Here again it is A minus B, means A plus 2's complement is equal to A minus B. After that we will again check the value of E. If E is equal to 1, then we will assign the Qn bit to 1. I will tell in further example what is this Qn bit and how we are changing its value. Now if E is equal to 0, then A is less than B, and we will again assign EA register to value A plus B. After that we will decrement the sequential counter value after performing one iteration, both from value. If we are getting the E from 0 is equal to 0, then again we are subtracting, decrementing the sequential counter. If we have E is equal to 1, at the end we are again decrementing the sequential counter value. Now this part is done. Now what we will get if E is equal to 1? If E flip-flop has a value 1, then again we have to set A register to A minus B, and A minus B again here performing by A plus 2's complement of B. First we will calculate the 1's complement, and adding 1 to there we will get 2's complement. So this is simply A is equal to A minus B, and after that we will check it means it is A is greater than equal to B, and again we are here changing the Qn bit to 1, and after that we will decrement the sequential counter value, and after that we will check whether the sequential counter value is 0 or not. If it is 0, then our division algorithm is over, and we will fetch the values of quotient from Q register and remainder value from A register. If it is not 0, then we will again go here and perform this again whole process again till we get the 0 value. So this is a simple example of this restoring algorithm. So what is the divisor here? Here divisor is 1 0 0 0 1. This is 2 raised to power 0 plus 1 2 0 1 2 3 4 plus 2 raised to power 4. So it is 17 again. 16 plus 1 17. This is a previous example, this which we have performed division algorithm, binary division algorithm. We have taken the same example again. This is the value, and this value is 148. So first task is we will store the dividend in A and Q. We will store the dividend in A register and Q register, and divisor in B register. Now this is B register. Now we will perform we have to use this 2's complement again and again. So we will calculate here in initial phase. So B is 1 0 0 0 1. First we will take its 1's complement, and its 1's complement is 1 to 0. we will simply flip the values 0 to 1, 0 to 1, 0 to 1 and 1 to 0. Now this is 1's complement. To obtain 2's complement, we will add 1 here. 1 plus 0 is 1, this 1, 1, 1, 0. So this is 2's complement, means it is the value of minus v. And we are using this in again and again on our algorithm. So we have to initialize sequential counter also. Now in Q we have 1, 2, 3, 4, 5 bits. So we will initialize sequential counter with 5. Now these are the action, these are the course of action what we have to perform. So the first action is shift left EAQ. So E is nothing here. Now we have to shift left. So this 0 of A come here, 1 come here, this 1 come here, this 1 come here, this 0 will come here, and this 0 will come here, 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 and this 0 will come here, and in last place we will append one more 0 after shifting left. Now the next step is we have to check the value of E flip-flop. Now the E flip-flop have 0 value. So we will go to this part, and in this part we have to perform E is equal to A plus B complement plus 1. We have calculated this B plus B's complement, 2's complement value here. So we simply add this value here 0, 1, 1, 1. Now what we will get? 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 2, and 2 in binary is 0, 1. So we will write 0 here and take a carry of 1 here. Now it is 1 plus 1 plus 1, which is 3. Now 3 in binary is written as 0, 1, 1. So we will write here 1 with carry 1. So in binary 2 is written as 1, 0 and 3 is written as 1, 1. So we will write 1 here with the carry of 1. Now 1 plus 1 is again 2. So we'll into binary is 0, 1. So we'll write 0 here, and 1 is get into E register, E flip-flop. After that we have to again check the value of E. Now we have reached here. In E we have to again check the value. If E is equal to 1, we have to go this part. If E is equal to 0, we have to go to this part. Now we are getting E is equal to 1. So we will move to this part, and in here we will write, we have to calculate, we have to assign Q1 bit to 1. Now what is Q1 bit? After shift left, we will get this value 0, 0, 0, 0. And we are appending 0 here. So this is Qn bit. This bit is known as Qn bit. So if we get value of E is equal to 1 here, we will change this value to 1. So this value 0 is flipped to 1. And after that we have to decrement the value of sequential counter. So sequential counter will be get from 5 to 4. Previously it was 5, now it is decremented to 4. After that we will check the value of special sequential counter whether it is 0 or not. It is not 0, then we have to again go to here. Now again we have to perform shift left operation. So to perform shift left operation, we will put this 0 here, this 1 here, this 0 here, this 1 here, this 1 is here, this 0 here, this 0 here, this 0 here, this 0 here, this 1 is here, and in last part we will put an extra 0. Now again we will check the value of E. Now E is equal to 0. So we will again move to here. We have to perform E is equal to A plus B complement plus 1, means A minus B. This is A minus B. Whether E is equal to 0 or 1, we have to add this 2's complement value in A. If it is 0, then some carry will be get passed to E, and if it is 1, then there is no value will get into E. So it is written as A is equal to A plus B plus 1. Now we get the value of, we were here, after performing this operation, we will get E is equal to 0. So E is equal to 0 is here, means A minus B. Now we will again add 2's complement here. Now the value of this is 0 plus 1 is 1, 1 plus 1 is 2, means 0 with carry 1. Now here 1 plus 1 plus 1 is 3, 3 means 1 with carry 1, 1 plus 1 is 2, means 0 with carry 1. And after that is 1, 1 plus 1 is 0 with carry 1. Again we will get the value of 1 in E. If E is equal to 1, then we have to set Qn bit to 1, means this 0 bit will convert it to 1. And sequential counter value will get reduced to minus 1, means 4 is decremented to 3. After that, we will again check the value of sequential counter. It is not equal to 0. We will go here. Again, we will shift left. So this value will get here. This 0 will get here. This here. After shifting these values, we will check the value of E. E is equal to 0. So we will perform add B's complement plus 1 here. After adding this, we will get this value. And E is equal to 0 here. If E is equal to 0, then we will go to this part. In this part, we have to leave Qn bit as it is. There is no change in Qn bit. And after adding B, it means it is a restoring remainder. After adding B, we will get E is equal to 1 here, and it is a restore remainder. We will again decrement the value of 2 and check the value of sequential counter. It is again not 0. We will again go to this part, sequential, shift left, and after performing shift left, we will get this 0 here, 1 here, 0 here, 1 here, 0 here, and here it is 0, 1, 1, 1, and last we will append one more 0. Now again we will check the value of E. Now E is equal to 1. So we will set the value of Qn to 1. This value of 0 is set to 1. After that, we will shift left EAQ. After shifting this, we will get this value. And we are checking the value of this E. It is 0. So we will add B plus 1 here. B complement means minus B here. After performing the addition operation, we will get E is equal to 0. E is equal to means 0 means we have to leave Qn bit as it is. After performing this, we will add B here. We will add B. After performing the addition operation, we will get 1 0 0 1 1 0. And we will check the value of sequential counter, which is 0. It means our algorithm has been ended, and the quotient, we can take the quotient from this Q register and remainder is stored in this register, and we can neglect the value of E. Now what is the value of this quotient? It is 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2 plus 2 raised to the power 4, which is equal to 26, and the value of remainder is 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2, which is 6. As previously we have done the binary division and decimal division, we will get the quotient value is 26 and remainder value is 6. So this is the complete algorithm. And now we are talking about the divide overflow. Now what is this, the divide overflow? So this, after performing the division operation, it may result in a quotient with an overflow. This is because the length of register is finite and we will not able to hold a number that exceeds the standard length, because our register has 5-bit registers and we can use only one register to hold the divisor and two registers to hold the dividend. The quotient will consist of 6 bits and if the 5 most significant bits of the dividend constitute a number greater than the divisor, then the quotient is to be stored in a standard 5-bit register. So the overflow bit will require one more flip-flop for storing the 6-bit. So this divide overflow condition must be avoided in normal computer operations because the entire quotient will be too long for transfer into a memory unit, that is words of standard length, that is the same as the length of register. So when the dividend is twice as long as the divisor, the condition of overflow can be stated as follows. A divide overflow condition occurs if the higher order of half bits of the dividend constitute a number greater than or equal to the divisor. So overflow condition is usually detected when a special flip-flop is set, and here special flip-flop is called as DVF, divide overflow flip-flop, and it is labeled as DVF in our algorithm. And the occurrence of a divide overflow can be handled in a variety of ways. So it is a responsibility of programmers like take a corrective measure such as rescaling the data to avoid overflow. We can simply divide stop, but it is a time consuming. We can also provide an interrupt request, suspend the current program and branch to a service routine to take a corrective measure. And the other algorithm for divisions are restoring method and a comparison method. Thanks.